Welcome everyone to the 2024 Photonics Spectra Summit Series. Thank you so much for attending the Raman Spectroscopy Summit, and in this session you'll hear from Rasmus Sterobo, an OEM spectrometer application specialist at Ipsen Photonics. Rasmus has experience in optical engineering, data conditioning, and implementing OEM spectrometers in high-performance optical devices. Today he's joining us to highlight spectrometer design principles for advanced applications. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's sessions, you can always come back later and watch it on demand. That's all from me, Rasmus. We appreciate you taking the time to join us today.
Yeah, thanks for having me on. Yeah, as mentioned, today we'll be looking at spectrometer design principles, mainly focusing on Raman spectroscopy as the main application. But of course, most of these things are applicable to more than one discipline. My name is Rasmus, and I will be presenting for you today. I've taken the liberty of splitting the presentation into three different parts. First, we'll have a brief introduction into the factors and characteristics that's related to Raman, specifically what the spectrum would typically look like and what to be aware of and what not to be aware of that much. Then we'll move into the kind of main portion of the presentation, which is the design and the technologies that goes into designing such a spectrometer, what factors to consider, what's important, when are they important, so on and so forth. And then we plan to conclude with some examples and different design philosophies, how we basically put all these things together into a coherent spectrometer design platform at the end of the day. So without further ado, I'll be jumping to the next slide. There we are. And as we know, it's a shocker, but light can interact with matter. That's kind of a known fact. And Kirchhoff's law tells us that it can essentially simplified do this in three ways, as we can't create nor destroy energy as such. So the first way light can interact with matter is that it can basically ignore it, be transmitted straight through, as shown here for an oxygen sample of an oxygen atom, or molecule rather, where the red and the yellow light is just passing straight through it, not really seeing the oxygen there. Then it can be absorbed. If you have a light of a specific wavelength, you might interact specifically with the electrons and the electron orbitals, and you might excite one electron up to a high orbital, and then the photon energy is kind of donated to exciting that electron, and the photon itself is lost. Might later be re-emitted via some other emission event, such as phosphorescence or fluorescence, but right now it's lost. And then finally, we have, of course, scattering, which also includes reflection, which is very typical, of course. Everybody's familiar with that. And that's where you have the photon of light comes in and it changes direction somehow. If it's reflected, that direction change is dictated by the laws of reflection. Basically, angle of incident is equal of the angle of exit as well. But it can also change direction into some other direction than that, where it's just generalized as some other scattering events. There are many different types, but they basically divide into two main portions: elastic scattering, where the energy of the photon is conserved, and inelastic scattering, where the energy of the photon is somehow changed. And this is basically where we get some of our Raman effects for, as we shall see here on the next slide, is that there are three main types of scattering we're dealing with when dealing with a Raman spectrometer. Rayline scattering, which is not what we're interested in, but unfortunately is much more common than the Stokes and anti-Stokes scattering, which generates the Raman signal. Rayline scattering is an elastic type of scattering. It's shown as the energy levels here in the diagram to the right, where you have the ground state energy, E0. You have a green photon that comes in there, it excites, it interacts with some of the electrons, they're sent up temporarily into a high energy state and comes right crashing down back to from which they came. And the energy is returned again as a photon with the exact same energy, but a new direction. That's Rayline scattering. It's not as common, of course, as reflection. It occurs about 0.1, 0.01% of the time. So basically 5 orders of magnitude less common than the intensity of the light incident. But of course, that would be something like the laser used in a Raman system. We're not really interested in that. We're interested in the Stokes and anti-Stokes scattering, which are an additional 3 orders of magnitude lower than Rayline scattering in intensity. And that's what you see in the middle. That's a typical Stokes example. Some energy comes in from a photon of a laser, and it then drops to a lower energy state, but not as low as before. It's somehow some of the energy excites a mode of vibration in the spectrometer, in the molecule, and that loss of energy translates into the photon being redshifted, basically having a longer wavelength when it enters the molecule. The opposite can also occur, where it starts out at a higher vibrational state and it drops back down to the ground state that's called anti-Stokes. And the difference in energy is the same, but it's shifted either towards a higher energy level, i.e. the photon will be blue shifted. And those generate our Raman signal. That's basically the Raman photons that we are interested in measuring. And because these states are discrete, we get discrete peaks that reflect them. And it's worth mentioning here as well that the likelihood of this occurring is proportional to 1 over to the power of 4 wavelength. So the shorter the wavelength of the incident light, the more likely it is that a Raman photon will be generated, basically. So you want to use shortest wavelength as possible for the laser if you want more Raman signal, but there are other downsides to doing that, which we will touch on in a moment. But that basically sums up a bit about the actual Raman spectrum you get as well. You have here an example of a Raman signal that's generated, and as told before, you can see they have these very high resolution spectral peaks in the actual spectrum itself, and each of those peaks represent a vibrational mode of the molecule, and that gives kind of a barcode or fingerprint of the molecule because these vibrations are unique to the individual molecule. But because this is a very rare event, comparatively speaking, you have a low photon count. So you need something that's very sensitive to actually detect it. And you need to be careful that you don't have this effect overpowered by some other effects, such as fluorescence or ray light scattering or what have you. It's worth also mentioning here that it's polarization dependent, in that the polarization of the light incident does affect how likely an event is to happen, as it needs to interact with the electron cloud of the molecule itself. So that is worth considering. And of course, up until a certain point, the intensity of the Raman signal scales with the intensity of the laser used to generate the Raman signal. So if you double the intensity of the laser, you should also get double the intensity of the Raman output, of course. But there are limits to how far you can go with laser power. If we move on to the next one here, now that we know a little bit about how what a Raman spectrum would look like, it's worth considering some of the design factors that goes into choosing the right tool for the task, essentially. And the first point we would recommend starting at is looking at what are the characteristics of the materials we want to be looking at. Does it suffer from fluorescence? Does it scatter a lot? So the Raman signal is strong for this kind of material. How many modes are there? Translate into how many peaks are there, how much information is there, because that basically helps you determine what kind of wavelength region you'll be working in, what laser will you be using. As mentioned before, a short wavelength laser will generate much more signal, going from a 785 nanometer laser in RI laser to a 532 nanometer laser should 5x your signal strength. But for a lot of biological material, you have a strong fluorescence if you use a green laser. And that will overpower your Raman, so it's not really feasible to do that unless you you can either shift to a longer wavelength laser to get out of the fluorescent band, or you can look at anti-Stokes. That could also be a way around it. But once you've chosen your laser wavelengths, you need to look at the resolution that's required. That's based on the number of peaks, the materials. Are you willing to deconvolute individual peaks if they kind of combine together to form a more summed up structure, I guess? And what kind of wavelength region will you be looking at? Which part of the spectrum basically contains the information we are interested in, which again depends, of course, on the material we're looking at. It's a common phenomenon, at least we see, that a lot of people say, well, we're only interested in a very small portion of the spectrum, so that should make it easy to design a spectrometer. But it's actually most often not the case. It's easier to have something that has a lower degree of diffraction, basically contains more of the Raman spectrum than only a single part of the Raman spectrum. So there can be a little bit of give and take there in what would be practical, what are you interested in as a use of such a system, and what's easy for a manufacturer to design for you. Does it have a downside that you have basically a broader bandwidth than you need, or can you live with that from a cost perspective or a practicalities perspective? Then there is the intensity of the laser. Of course, as I said before, it should scale in theory linearly. But there is, of course, an upper limit on the laser power, both from a practical and safety perspective, but also from a perspective of you might damage your material if the laser is too powerful. And then finally, is the material, does it have strong polarization dependency on its signal? That might also influence your choice of technology. And having considered those factors, we can start looking at what the spectrometer actually needs to do. And the spectrometer in this case is essentially consisting of 3 individual components, I would say. You have the optics parts, of which there can be used mirrors, gratings, mirrors, lenses, or other optical components such as filters. You have the heart of the spectrometer in the form of the diffractive element, typically a grating of some sort. And then at the end of the spectrometer, you will have a detector. And choosing the right technology here is basically a matter of understanding what are we trying to achieve. And we can look at that a little bit more in details by saying, you know, the optical system itself, it's common to either use mirrors or use lenses as the optical systems building components, I guess you could say. And there are pros and cons to both. There's no right or wrong answers here, but considering the different strengths and weaknesses is of course a good idea to pick the optimal design. And mirror-based systems have the advantage that it doesn't suffer from any chromatic aberrations, as it doesn't interact with the medium itself. It's reflected from the surface, so you don't get a dependency. It's a purely geometrical things. You don't have a dependency on the specific wavelength as such. Mirrors are also, at least in most cases, lighter weight than a thick aspheric lens, and they can be quite cost effective in that sense as well. And not always the case, but often you can get a nice even resolution across your full bandwidth from the spectrometer. It doesn't mean that the peaks are symmetrical, but the width, the full width half maximum peak, can be very consistent across a broad wavelength range. If we instead look at the opposite, a lens-based system, well, it's often preferred in these instances because it can be used to have a limit astigmatism. So in a lot of mirror systems, you will see that at some wavelengths, the height of the spectrum will be taller than it will in others, and that can mean that you will be losing some light that won't reach the detector. And of course, with a Raman spectrum, you don't have a lot of light to begin with, so every photon really counts here. So you would typically use a lens system to limit this effect. They're also good with large numerical apertures. So if you're trying to fit in a large angle into the spectrometer, you can make an aspheric lens that can kind of handle that without too many aberrations. The shape of the peak, and it again depends on system design, can also be quite nicely symmetrical with lenses because you can make these more complex shapes, or typically they're at least easier to find with aspheric lenses. And you generally speaking also have more design flexibility, which is also present in these 2 examples I pulled up here, because even though both these examples, the left one, which is the 2 mirror systems, and the right one, which are 2 lenses, only have 2 optical components, 2 lenses, 2 mirrors, you actually have 5 surfaces in the one on the right, because we're using an achromatic lens as the first point of entrance, so there are 3 surfaces there. And for the aspheric lens to focus on the spectrum onto the detector, there are again 2 surfaces. So now we have 5 different design surfaces essentially, compared to just 2 in a mirror-based spectrometer. And I wanted to go a little bit more into details about some of the pros and cons and how this can be a little bit deceptive as well. Because if we took a theoretical system such as the grating mirror on the left here, and said that the resolution, it's very flat, it's very even, and it could even be higher than it could be for a lens grating lens in this theoretical sample. Let's say that the resolution, as mentioned here in orange, is around 0.8 nanometers, and for the lens grating lens, it's about a 1 nanometer resolution. Well, you would think that your Raman resolution would be, of course, be better with the one that has a lower resolution, but it depends on where that resolution is actually achieved. And if I go to the next slide here, we do see that I've painted in here in blue a resolution curve that's very flat for a mirror-based system, and one that's not so flat in orange for a lens-based system that has the resolution that's mentioned before. And even though the resolution for a lens-based system is about 1 nanometers at its worst in the middle here, when we actually convert that into what it would be in Raman resolution, wavelength shift, we actually see that the worst, quote unquote, worst resolution achieved is actually better for the lens system. But it depends on where you are in the spectrum, at what Raman shift basically we are looking at. And that's something to consider, because having just a single data point telling you that the resolution needs to be below 10 inverse centimeters or something like that doesn't necessarily tell the entire story. So it would be advantageous to always look at what portion of the spectrum are you in need of this resolution. Where is the most information packed, essentially? So do you need 10 inverse centimeters at, in the high wave numbers, or do you need them in the fingerprint region or somewhere in between? Because if you have something that has a nice flat resolution in optical resolution in nanometers throughout the spectrum, you will see that the inverse centimeter, the Raman shift resolution, is of course worse at shorter shifts or lower shifts, and will become better as you move throughout the entire wavelength range. So something to pay attention to for certain. And on that note, we can also look at the spectrum itself and see what kind of resolution is actually needed. This is an example I've taken of glucose in an aqueous solution. And as you can see, these are two spectrums that are acquired with similar spectrometers, but with different slit widths. And as to be seen, this type of spectrum, it does have some information that's, in the finer details, but the broad features of glucose is actually quite low res. It doesn't require the highest of resolutions. So I've overlaid the main portion. Some of the distinguishing features of glucose is at around 1,000 to 1,200 inverse centimeters. And looking at that, the resolution naturally from glucose is something like 50 inverse centimeters. So you don't need that high resolution. And that means you can move to a broader slit as the entrance. You can get more light through it. You can decrease measurement times. You can reduce cost potentially. And that plays back to the whole thing of looking at what are we kind of wanting to examine as the sample here, and do we need a certain resolution to actually measure that sample or not? Because in Raman, it's very easy to get hung up on we need a very, very high resolution, because most Raman spectrums have these very well-defined peaks, but especially for biological materials or more complex molecules, that's not necessarily the case. So it really pays to look into what a typical spectrum would look like. And moving on to the next slide, we have basically the heart of the spectrometer, which is the different grating technologies that can be used in a Raman spectrum, or in any spectrometer for that matter. Of course, the most commonly known of it would be something like the reflection-based grating, surface relief reflective grating, which is shown here to the left. This is a true and tested technology, of course, and it enables great design flexibility, because the tilt of the grating will affect the position of the wavelength diffracted by the grating. So it's really good in something like an experimental system where you are not quite sure what wavelength you want, or if you want something that's made to custom. It can also be good, because you can of course easily change the bandwidth that you're looking at by just tilting the grating at the cost of some efficiency naturally. The downside to this technology when it comes to Raman spectrometry is that it has a tendency to really prefer the S polarization of light over the P polarization, and that can of course, in something that's polarization dependent such as Raman, really be a deal breaker in some instances. Next to that, in the middle, we have volume phase gratings, which solves the problem essentially of polarization dependence, as does transmissive gratings in general. So that's also why they are very popular for Raman applications, as you can make them high resolutions, and you don't need to deal with the fact that one polarization is really preferred to another one. And at the very right, we have also a transmissive type grating with surface relief transmission grating. Now, unlike the volume phase holographic grating, the grating here is not embedded internally into the grating itself, it's rather on the top. But as we shall see, while that makes them more sensitive to being touched or more fragile in that sense, it doesn't really matter when they're built into a spectrometer, and it does offer some benefits when it comes to efficiencies, as shall be seen on the following slide here. Here what we're looking at is some typical gratings that would be used in a Raman spectrometer for a 532 nanometer spectrum. And we can start with the reflection-based grating, which is shown here in orange. The unpolarized light starts out with a diffraction efficiency of around 60%, goes down to just below 50, it's a very nice and even curve. It's not the highest efficiency, but it's at least very even throughout the entire spectral range. What is really notable here is, as mentioned before, is that the one polarization, the p polarization, is preferred to the s polarization. So as you move through the bandwidth of the spectrometers towards 600 and 700 nanometers, you see that the one of the polarization really separates out, and you get a strong preference from one rather than the other, which for some applications can be really problematic. And volume phase grating here shown in red solves that problem, essentially, as does surface relief transmission gratings. Now, the downside to something like a volume phase grating for these applications is there's not a big difference in the optical index between the exposed and non-exposed gel in a volume phase grating. And that means that the bandwidth of the grating is gonna be lower than it is for surface relief grating. And you can see that here that it starts out very high at 90% efficiency, but it drops down quite quickly, and it actually ends up around 20% efficiency for this theoretical design. And that's due to the grating essentially having to be thicker. The actual gel itself has to be thicker due to it having a lower change in indice, the refractive indice. As a rule of thumb, we say that the bandwidth can be around 12% of the central wavelength. So if you have something where the central wavelength was at 1000 nanometers, you would have a bandwidth where it's above 80% efficiency of around 120 nanometers. That's just the rule of thumb. Because there's a high refractive indice change for a surface relief grating, shown here in green, that goes up to 36%, essentially. And that's why you can get something like shown here, that's above 80% all the way throughout the 200 nanometer bandwidth. And these are for gratings with the resolution that's typical for Raman spectrometers. So both the reflective grating and the VPH grating here are 1800 lines per millimeter gratings, whereas something like the surface relief grating here can actually be manufactured with even higher resolutions and still maintain its diffraction efficiency. The example shown here is at 2200 lines per millimeter, for instance. And the reason why the resolution of the grating or the lines per millimeters matters is because it allows for the design to become more compact and use smaller optical components, become more lightweight. So what we're looking at here is a simulation, and although these are only sketches, they are to scale of 3 different designs that have the same bandwidth of 800 to 1100 nanometers, typical 785 nanometer Raman spectrometer with the same resolution. But the one change that's been done here is that the grating has been changed. Design C, shown all the way here to the right, is modeled using a 900 lines per millimeter grating. Design B in the middle is 1200 lines per millimeter. And the design A, which is by far the smallest one here, is 1500 lines per millimeter. And as the diffraction angle changes, it means that the focal length of the lenses has to be smaller, doesn't need to be as long for the light to be spread enough to get the same resolution and cover the full detector. And that's of course advantageous because it allows for smaller design while not compromising on the resolution of the spectrometer or the data points. The limiting factor here is typically how high an efficiency can you get from a grating while going into a high resolution. That's typically what will be the limiting factor. But if you can get a high resolution grating that has great diffraction efficiency, that's certainly the way to go. Finally, for a spectrometer to consider, there is of course the detector itself. And for that, you need to consider the efficiency of the detector, the noise, and the stability. It depends on how much signal do you have to work with. If it's very low signal counts, your detector might have an excellent signal to noise ratio, but that only really comes into play typically the numbers that's rated once the detector is near saturation. So if you're not working in a near saturation environment, you actually need to look more at something like the read noise, because that's probably going to be the dominating factor. When it comes to stability, thermal regulation is of course typical and normal for Raman detectors. How much you need to cool them depends on the length of your exposure time and the type of technology you use. If you use something like a deep depletion CCD, it's a thick layer of bulk silica, you need to cool them a lot more than you need with a standard backfin CCD. So it's something to consider whether your exposure times are long enough to need this deep depletion, deeply cooled, or whether you just need the stability and can go with something that's a lot more cost effective to work with and also more practical in the real world. But that depends again on the application. To conclude, we'll be looking at some of the system constraints. Now, designing a Raman system has shown here an example of what that could look like. It's a bit like riding a bike in that you have three main points of interaction. For a bike, that would be the pedal, the saddle, and the handlebar. For a Raman system, same is true, 3 points of interaction. You have your laser fiber that comes in somewhere, your laser that is generating your Raman signal. You have an interaction with the material that you want to probe. And you, of course, have to take that generated Raman signal and put it into a spectrometer so you can measure it. Now, how you go about this depends on what are your constraints of the system. Typically, you have a laser that you want to use, and it can come in many different configurations, but it wouldn't be unusual for them to have like a 50 or 100 micron fiber. And that's with a 22 Na output. You could, of course, use a similar input for the sample. You end up with a spot size that's again 100 micron 22 Na. But what if you wanted to have a larger numerical aperture? If you put a large numerical aperture lens, a spherical lens in front of your sample, it's gonna make the spot size smaller. And that might be advantageous. You might want a small spot size, but it can also be problematic if you end up in a situation where the intensity is too large. You're gonna burn your sample. So an example of this is where you can basically trade a large numerical aperture for a larger geometrical aperture and make the system more practical in the real world. And we made an example of this here where look at again at a 22 Na input fiber, 100 micron green laser, and you send that through a lens condenser, a spheric lens with a 3 times larger Na. If you only use if the focal lengths are the same, it's basically the diameter of the condenser lens that's larger than the diameter of the collimation lens for the excitation laser. So you end up with a spot size that still has a 22 Na, still 100 microns large, but now you can collect Raman signal from in this instance, 0.6 Na, 3 times the size of Na, and of course, the size of the Na scales by the square root. So 3 times the Na means you can collect for 9 times the area, basically, when it comes to angle, 9 times the power if the power is evenly distributed. And putting a 0.6 Na into a spectrometer is not that practical. So typically what we would do is you could use a lens that has 3 times the focal length, crop that down from a 0.6 Na to a 0.2 Na, and then put it on a 3 times the size geometrically fiber. So what we would recommend, or what would be a good solution here, trading an Na for geometrical aperture instead, put it on a fiber bundle with 7 fibers in it, typical standard 0.2 Na, and take that round fiber bundle into a linear one, so the coupling with the spectrometer becomes really, really good. Now you have something that's about 900 micron tall, and that fits with a lot of low noise detectors. So you get excellent cropping and you get a large collection area. So you kind of, getting the best of the both factors here that you're interested in. But again, it depends on your constraints of the system. But these are the design factors that goes into some of the spectrometers we design, and we try to use kind of these factors as being important milestones in what we want to achieve. Of course, the performance, the form factor, and reliability all needs to come together. So if the performance isn't good enough, it's of course not going to be of interest. So you can deliver some of these spectrometer, or we can deliver some of these spectrometer with performance where resolution is down to 5 inverse centimeters. The coverage is anything from the fingerprint region to high wave numbers over a large detector area. But because you with surface relief technology, transmission grating technology can make these high resolution gratings, you can make the package a lot more compact than you would typically find. And you can also make it very environmentally stable and thermal robust in design, so these designs can be taken and used in the real world. And by that, I would like to conclude. If there's any questions or any interest, please reach out to us or meet us at Optitech. We will be there in May, so hope to be back from you.
Thank you so much, Rasmus, for joining us to detail spectrometer design principles for advanced applications. To everyone in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Raman Spectroscopy Summit. Thank you all so much for joining us.